Welcome back to another video of our course, Measure Theory for Probabilists. We saw that it's relatively easy to define a set function on, let's say, a semi-ring, which we could then also extend to a set function on the ring generated by the semi-ring. However, we would like to introduce measures which are defined on the sigma algebra, defined through the semi-ring. And today we are going to learn how that can happen. So we start off with a set function on a semi-ring and want to extend this using outer measures, for example, to a measure on the sigma algebra generated by the semi-ring. So let's start. That's the plan for today's video. So H is usually a semi-ring, and we are asking when can a set function mu on the semi-ring be uniquely extended to a measure on the sigma algebra. So we need two things, existence and uniqueness, as so often in mathematics. So we need an extension, existence, and we need it to be uniqueness. Let me just start with uniqueness. Here we will have the following very important result, which states that if you have an intersection stable generator of the sigma algebra, sigma of H, then two finite measures or sigma finite measures coincide if and only if they coincide on the generator. And H is, for example, a semi-ring. That's easy to check, usually. And from this, we already know that these two are the same. So that's uniqueness, and here it's important that's here intersection stable. Okay, we will try to prove this, and that's uniqueness. For existence, we will have the so-called Carathéodory's extension theorem. So we have two results here, 2.13 and then 2.16, which I will mention in a second. We will use outer measures. They were studied a lot by Carathéodory. I will recall them on the next slide. Outer measures, and we already had measurable sets. So measurable sets with respect to the outer measure mu star. And we will show that they form a sigma algebra. We will also have that the mu star measurable sets contain this H we have here. And since that's a sigma field, sigma algebra, then also sigma of H, all elements of sigma of H are measurable sets, and then we basically have it. So, okay, that will require some work and some more understanding how all this works. Let me come to this starting on the next slide. But before this, let me give another overview. Okay, outer measures come on a later slide. So here are the results that work together in all this. Here the empty circles are assumptions of the corresponding results, and the filled circles are then the conclusions. So for example, lemma 2.5 we have a sigma additive set function on a semi-ring which is sigma additive, then it's also sigma subadditive, and the other way around. We had this. So what we basically want to have is that mu extends uniquely to sigma of H. So this here we want to have. That's what we want to have as conclusion. So what do we need? Theorem 2.16 tells us we need a sigma finite mu defined on a semi-ring, which is sigma additive. That will be the result. How can we have a sigma additive set function? For example, here. we need an additive finite set function on a semi-ring which is in a K regular where K is a compact system. We had that result last time. That's how we could conclude here what we want. Unique extension to sigma of H. We could also have that we have an additive set function defined on a semi-ring which is sigma subadditive. Then it's also sigma additive. Then we have these three things. Mu has to be sigma finite. Then we also have this here. So basically we want to come to this conclusion here and either need lemma 2.5 or theorem 2.10. Okay. As mentioned on the first slide, let's start with uniqueness. So that's basically this result here. So I wrote it down again. So H is an intersection stable generator of sigma of H. I have sigma finite measures. Then they coincide if and only if they coincide on the generator. I give a partial proof. The full proof is in the manuscript, just for simplicity. So I assume that the measures here are finite. They're finite with the same value for the whole set. For example, both could be probability measures. Then I would have mu of omega is 1 and mu of omega is also 1. That would be one case, and that's exactly the case I'm most interested in. I have an if and only if, and one direction is clear anyway. So if they coincide, they also coincide on the generator. That should be no surprise. The other way around is more interesting. Let me define a set system for this. So D is the set of B's such that mu of B equals nu of B. Of course, that's a superset of H, because all B's in H have this, because we're going from right to left, so mu and nu agree on H. We are going to prove, so to show, we are going to show that D is a Dynkin system. Yeah, why is this important? So if D is a Dynkin system, let me just try to find this. We had theorem 1.13. However, was this? Not here, but probably here. That was theorem 1.13. We had D is a Dynkin system. The C here is our H, and H has to be intersection stable. Then sigma of C is a subset of D. Yeah. So when we have this, so let's see this. So let us show that the H is part of D. So that's our goal. No, H is part of D. We already have this. If we now then also have that D is a Dynkin system, we can conclude, so from this here, we can conclude that sigma of H is subset of D from the theorem 1.13. And that's what we want. We want that all elements in sigma of H, so these are all elements we need in order to see that mu and nu coincide. So if sigma of H is part of D, you would have that sigma that mu of B equals nu of B for all B in sigma of H. Well, and that's exactly what we want here. So we only need to show that this D here is a Dynkin system. So again, what was a Dynkin system? Here, Dynkin system we must have that the whole set is in this here. Okay, that's easy in our case because we assume this here. We assume that mu of omega equals nu of omega, so omega is part of D. D has to be set difference stable for subsets. So if A is part of B, and then B without A is in D, and so on. And also here, if they're increasing, that their union is also in D. So these two things we still have to show. So if we have B and C in D, and B is subset of C, what happens? Then mu of C without B, well, this is mu of C minus mu of B, because the mu here is a measure, so it's additive, and B, this joint union with C without B is C. So this here holds. We have assumed B and C are in D, which means mu of C equals nu of C, mu of B equals nu of B, and this again is nu of C without B. So we have shown that nu of C without B is nu of C without B, and that means C without B is also in D. So that's the second property of the Dynkin system. And for the third one, we need an increasing sequence of sets, B1, B2, and so on. All are in D, with B1 subset of B2 and so on. And B is the union n from 1 to infinity of the Bn's. Yes. So this is certainly in sigma of h. I think. So that's in the sigma algebra on which mu and nu are defined. We have to prove that B is also in the Dynkin system D. So that's our task now. Mu of B. First of all, we know, because mu is a measure, that this is the same as the limit mu of Bn, n to infinity. Because as a measure, as a sigma finite measure, it is sigma additive. And we showed last time, I think, that sigma additivity is the same as continuity from below, which is exactly this here. Mu of Bn, mu of Bn is the same as, what happens here, is the same as nu of Bn, because the Bn's are in D. Well, and since nu is a measure, that is nu of B. And so everything is done. We know that B is in D. We know, therefore, that D is a Dynkin system, and we are done with this important proposition. Okay, so that was the first part. That was the easier part, actually. Uniqueness. Now we have to come to existence here. And as you see here, we have outer measures and measurable sets and so on. So what again was this? Here is something which we already had on one slide where we introduced the outer measures. An outer measure is a sigma subadditive monotone set function on the power set of omega with a property that the empty set maps to 0. That's what we already needed. But what we never needed until now is the second thing. These are the measurable sets. So mu star measurable sets. So when is a set A mu star measurable? It's mu star measurable if and only if for all e's. So these are really many. For all e's, mu of e equals mu of e without a plus mu of e and the complement of a. And let me mention some things here. E intersection A union E intersection A complement. Okay. Here you only have elements in A, here you only have elements in A complement, which means that's a disjoint union, apparently. And a union, so that's a union, and mu star is subadditive. That means that the union of these two things equals E. Well, so that's E. And mu of the union is, in any case, smaller or equal to the right-hand side. So that's for sure, always. The question is if the other way around also holds. So I could also write down this here with this unequal sign, and it wouldn't change anything because the other way holds by assumption. But I won't do this. But just to see that this equality has basically two directions, smaller equal and bigger equal, and one of them is always trivial. So that's mu star measurable. And we're going to prove this theorem first. We have an outer measure. Then the set of mu star measurable sets is a sigma algebra. Well, that's really nice. So the elements here which fulfill this equality for all e's, that's a sigma algebra. And therefore, we can restrict the outer measure, which is defined on the power set, to the sigma algebra F star, and that's a measure, apparently. Well, and also, that's a side note, the sets which have outer measure 0 are always measurable with respect to the outer measure. Okay. So let's start the proof. So what do we need to show? So we have to show that the set of mu star measurable sets is in fact a sigma algebra. So first of all, the empty set is in F star a claim. Why is that? Well, what do we have to show? We have to pick any E, and mu star of E has to be the same as mu star of E intersection with the empty set plus mu star of E intersection with the complement of the empty set, which is the full space. And of course, this here is E, and this here is the empty set, which means that because we have an outer measure, this here is 0. Well, and now it's trivial. So here are just the two same things. So the empty set is always measurable. Then if A is mu star measurable, I won't even show, but just say that's trivial, that the complement is also F star measurable. Why is that? If this here holds and you replace A by the complement of A, yeah, the right-hand side doesn't really change because here I have an A complement, which is this term here. And the complement of A complement is A. Well, the roles of these two terms just change. So that's okay. Then we have to prove that if A and B are measurable with respect to the outer measure, then their intersection is also measurable. Why is that? Well, that's now a computation. So I will write down mu star of E, and E is again some arbitrary subset of my whole space. I can use that A and B are measurable. For example, for A, that means that this here is the same as mu star of E intersection with A plus mu star of E intersection with the complement of A. Now I can use the following. I mean, this here, E intersection with A, I can use as this E here in the measurability property. Oh, yeah. That means that this here must be the same as mu star of E intersection A intersection B plus mu star E intersection A intersection B complement. So now I've used that B is mu star measurable plus mu of E intersection A complement. And now let's look at the last two terms here. Here, side note. E intersection A intersection B complement union E intersection A complement. Well, what's that? So, okay, all elements must be in E. They're either in A but not in B, or they are not in A. And that means they are in the complement of A intersection B. You can also go through this more slowly, but that's what comes out. Yeah, so wait. Yeah, that's okay. That's okay. So, okay, what's in this set here cannot be in both A and B, because if it's not in, if it's not in A, it's not here, but if it's in A and not in B, it's in here. So yeah, that's essentially the same. So that's just the same. So the union of these two here is this here. And by subadditivity, that's here bigger or equal than mu star of E intersection A intersection B plus mu of E intersection A intersection B complement. And again, the union of these two here is just E, which means that I can write further mu star, forgot the stars here, of E, like this here. And now we have on the left-hand side and on the right-hand side the same. So all terms must be the same. Which means that mu star of E equals this middle term here. And this here means that A intersection B is in F star. So A intersection B must be in F star. Okay, so we have intersection stability of F star. Now we need stability under disjoint unions. Yeah, so that's the next thing. Let me make some space. So, well, we proved this here, right? We proved this here. So next we have A1, A2, and so on. They are all in F star. And they're disjoint. Bn is the disjoint union of AKs, k from 1 to n. Also in F star. And Bn's, they increase to a B. And my claim is, what I need to show is that mu star of E intersection B is the same as the sum, Bn, sum k from 1 to n, mu star of E intersection AK. Okay, so E intersection Bn is the disjoint union of E intersection AKs, apparently. And I need to prove that this sum formula holds. And I'm doing this by induction on n. And for n equals 1, that's pretty trivial, because Bn is V1 is A1, and the two terms are just the same. And let's just assume we already have that proved here for some n. And we want to have it proved for n plus 1. Well, like this here. I did mention one thing. So we already proved that F star is complement stable and intersection stable. And that means it's also union stable, because the union of complements is the complement of the intersection or something. That means the Bn's are already in F star. We already have this. All Bn's are in F star. I can use here that the Bn plus 1 is in F star. So it's mu star measurable, which means, I need that Bn is mu star measurable. In order to write, that's the same as mu star of E intersection Bn plus 1 intersection Bn plus mu star E intersection Bn plus 1 intersection Bn complement. The Bn's here apparently increase. So Bn plus 1 is bigger than Bn. And this here is just E intersection Bn. Mu star E intersection Bn. And here that's Bn plus 1 without Bn. When you look at this here, Bn plus 1 without Bn is just An plus 1. Plus mu star E intersection A n plus 1. Now we can use the induction hypothesis. So this here is already the sum here. And we're just adding the next term. And we have that that's the same as sum over k plus k from 1 to n plus 1 mu star of E intersection AK. So we have proved this formula here. Okay. We now want to extend this, so we have Bn here, but we would really like to have B's here. And the B's are the disjoint union of the AKs. So B is the disjoint union of AKs, k from 1 to infinity. So let me write this down. Mu star of E intersection B. What can I do with this here? B is a disjoint union. So that is here is a union. And we know that mu star is sigma subadditive. So I can write this as small or equal, k from 1 to infinity, mu star of E intersection AK. This here, by definition, is a limit n goes to infinity. Sum k from 1 to n, mu star E intersection AK. This here we just computed is mu star of E intersection Bn. This here equals limit n goes to infinity, mu star of E intersection Bn's. And now E intersection Bn, because the Bn's are increasing by monotonicity of mu star, that's small equal than mu star of E intersection B, which is the same as on the left-hand side here. So, for example, we have proved that these two things here, they coincide. So we have proved that these two here are the same. Yeah. And this here is also the same. We also proved this. Okay. We are still on our way to show that F star is a sigma algebra. We proved that the empty set is an element. If A is in the empty set is in F star, we have shown that if A is in F star, the complement also, it's intersection stable, therefore also union stable, but we still have to see that it's sigma union stable. And that means we have to show that the B here, so B, which is the union of the AKs here, that's also in F star. So B is in F star, I claim, since, well, mu star of E, because Bn is mu star measurable, that's the same as mu star of E intersection Bn plus mu of E intersection Bn complement. That works for every n, so it also works for n goes to infinity. We have shown that this limit here equals this. That's what we have just shown. Mu star of E intersection B. The Bn's are increasing, which means that the complements are decreasing, such that I make this at most smaller if I write down mu of E intersection B complement. Right? And this here, as we had a few times now, is small or equal than mu star of E, because the union of these two here is E. So that's the union, and mu star of the union is small equal than the sum of the mu stars. So we have shown, again, mu star of E here, mu star of E here, all these are the same. In particular, we have shown that this here is the same as the sum of these two, which means that B is F star measurable, so B is in F star. Okay, great. Basically, we now have it. We have shown that F star is a sigma algebra. I think I left out one step. For sigma algebra, we would have, so this disjoint union here is maybe not what we want. But if Bn is just a regular union, we can just write Bn as a disjoint union by saying, well, Bn, so replace, okay, A1 is okay, replace A2 by A2 without A1, replace A3 by A3 without A1 union U2, and so on. So it's not less general if we have here a disjoint union in order to show that F star is a sigma algebra. That's one thing. So F star is a sigma algebra, and we showed also here, where is this? So basically here, we showed it here. So take E as the whole space. We showed that on F star, we have sigma additivity, because this property, I mean, they're equal. That's just sigma additivity, because B is the disjoint union of all these AKs here. So we have shown that mu star is sigma additive, additive on F star. That means mu star restricted to F star is a measure. Okay, and that was it almost. We have one more thing. There's null sets here. So sets with outer measure 0 are measurable. That's what we still need here. That's the last bit of theorem 2.13. That's relatively easy. So if we have an n, which has mu star of n equals 0, and any e, then mu star of e intersection n must be 0, because mu star is monotone. And this here is a subset of n, and mu star of n is 0 anyway. So we can write the following: mu star of e intersection complement of n plus mu star of e intersection n. First, that's bigger or equal than mu star of e, because the union of these twos, that's e, and subadditivity of mu star. This is apparently bigger or equal than mu star of e intersection with something, which I now take here as n complement. And this here is the same as mu star of e intersection n complement plus mu star of e intersection n, because that last number here is 0 anyway. So we have the same on the right and left hand side, which again means everything is the same. In particular, mu star of e equals this here, which means that n is element of F star. It's measurable with respect to the outer measure. Okay, so that was the most important part. And now we want to take advantage of all this. So, remember, our initial goal was we have a a set function, additive set function on a semi-ring. And we want to define a measure from this. And we do it like this. We define an outer measure using this, and then restrict the outer measure, as in this result here, to the set of measurable sets, which is the sigma algebra, and we then have a measure on the sigma algebra we want to have. And that's the first result here. So that's more, well, it's a definition, it's a proposition, but first of all, it's a definition. So an additive set function on a semi-ring defines a set function on, well, A here is any subset of omega. So mu star here is defined on the power set of omega. Well, that looks complicated. Maybe draw a picture. So this is here my A. And I want to define mu star of A. What do I want? Well, I say I'm going to cover this. I'm going to cover this here with sets. I'm going to cover this with sets, the A here. All these sets that are the sets G. And the G's are in, well, script G. And the script G here is at most countable. The G here, in addition, is subset of my H of my semi-ring. So the G's are, so they're all elements of the semi-ring, which means I can compute mu of G. And I can add all this. I can add all the mu of G's. And I do this as tight as possible, meaning that I'm trying to cover my A as good as possible by a countable number of sets within the semi-ring. And I'm adding these countably many volumes as good as possible. That's the infimum here. And then I have the value of my outer measure. Well, so it's an outer measure that really makes sense here because I'm approximating it from the outside. So the sets G here, they have to cover all of A and maybe a bit more. Yeah. The claim is this is an outer measure. So what was an outer measure again? Let's look. Mu of empty set is 0. Subadditive, sigma subadditive, and monotone. Okay. First, well, mu star of empty set is 0. That's easy. Because I can just say the G here is well, it's one element which is the empty set. Okay, one element which is the empty set, and since mu is additive, the empty set has to have value 0 because yeah. Oops. This here is the same as mu of empty set plus mu of empty set. Because of additivity, these two here, the union is the empty set. So that's just a very trivial statement on additivity. So that's 2 times mu of empty set. Well, and if you look at this equation here, that can only work if mu of empty set is 0. Well, or infinity, but infinity is excluded here. Okay, empty set is 0, that's fine. Monotone, okay, that's also fine because if you have another set, well, B here, let's say I have B here, which is smaller than A, then any cover of the G's here of A is also cover of B here, which means that when I compute mu star of B, the infimum I take here is over a larger set, which means the infimum is smaller. That means mu star must be monotone. Monotone. That's also okay. So let's come to sigma subadditivity. Well, sigma subadditivity. Here we take A1, A2, and so on. Well, and I claim I can do the following. For each of these ANs here, I can take a KN at most countable, and I can take GN Ks, well, K in Kn. All of them are element of my semi-ring, such that, first of all, the AN is covered by the GNKs, GNK, K in Kn. So the N is just fixed here in all this. But the picture is like this here. The AN is covered by the GNs. The G's are have an index K here. I can do it such that mu star of AN, that's what I claim, is bigger or equal than the sum K in Kn mu of GNK minus any epsilon that I want. For example, epsilon times n 2 to the minus n for any epsilon which I'm setting before. Okay, let's just look at this here for a moment. N is fixed, and that's just some epsilon. Yeah, I have this infimum here. And the infimum here means that if I increase the right-hand side by a little bit, I really do find such a set G of sets G in my semi-ring, which cover my A. Yeah. So the infimum over all these possibilities, that's mu star of AN. And if I allow for a little bit of space, so this here decreases to this here, but now I subtract something, then I can get something which is in fact smaller or equal than mu star of AN. Okay, that's by the approximation property of this sum here to this mu star of A. Like this. And now I have mu star of the union AN, n from 1 to infinity. Then what do I know? What do I know? Well, I know that this union here is covered by all the G and Ks for N and K running. So by definition of the outer measure, that's smaller or equal than n from 1 to infinity, sum K in Kn, mu of GNK. And now this term here appears, which means that this here is smaller or equal than sum from n from 1 to infinity, mu of AN. plus epsilon n to the minus 2. I'm summing over all n, so I have here plus epsilon, and epsilon was arbitrary. Okay, for all epsilon bigger than 0, I have this inequality, which means mu of the union must be smaller or equal than the sum of the mu ANs, which is sigma subadditivity, and we are done. Because we've proved that mu star has all the properties what we need for an outer measure. Okay, and now we come to theorem 2.16, which was mentioned on this overview here. So this here we wanted to extend mu uniquely to sigma of h. So we have a semiring. We have an additive sigma finite set function on this semiring. We have mu star defined here. We can restrict mu star to f star, which was in theorem 2.13, set of all mu star measurable sets. That's a sigma algebra. Then what we still need is that sigma of h is subset of f star. And mu star restricted to sigma of h is the only measure that agrees with mu on h. So what do we need? We need basically two things. So we need, for example, mu star, mu tilde agrees with mu on h. And mu star, mu tilde is the same as mu star. It's only a restriction. Yeah. So I need to show if h is in the semiring, then mu star of h equals mu of h. Well, yeah, I can choose a k countable, k subset of the semiring, at most countable. With h is a subset of the h k's, k in k, and as before, mu star of h is bigger or equal than the sum mu of h k's minus epsilon k in k. So what's the point here? So I want to compute as good as possible the mu star of h. You might be tempted to think, well, mu star of h, that must be, well, the g I just take here as a singleton, which is my h itself. So mu star of h equals mu of h, and I have it. But as the definition here shows, it could be that I can cover my h by using countably many sets in my semiring, such that this here gives an even smaller number. That's not prevented. And that's why we need this here. So if it does this, I can still argue as here, h is the subset here, and this here is maybe smaller than mu star of h. Well, like this here. But that cannot really be the case, as we will see. First of all, what can I say? I can say mu star of h, first of all, must be smaller or equal than mu of h. Because h covers the h, which then, well, so it's mu of h is an upper bound for mu star of h, because this infimum can only be smaller than one concrete value for this thing here, which is mu of h if G has just has one element. So that's the first thing. Then a semiring. So what I have is the semiring is sigma additive, right? So H equals the disjoint equals the union of mu of HK intersection with H. I sum over all K in my K. So the union of all this is this here. Yes. And mu of a union is smaller or equal than this here, because we already have that sigma additivity of this sect function here implies sigma subadditivity. We had that in one of the last videos. This here is smaller or equal to, because of monotonicity, mu of hk, k in k. And this here is smaller or equal than, well, like here, mu star of h plus epsilon. Mu star of h plus epsilon. Epsilon goes to 0. That means all of this here is the same. Which in particular means that mu star of h equals mu of h, which is what we wanted to show. Okay. The measure agrees with mu on h. We already have this. What we still need is that h is subset of f star. We need to show that the sigma of h is subset of f star, but that here is enough. F star is a sigma algebra. So if h is subset of f star, then sigma of h is also subset of f star. And the argument is similar. So what do we need? We need that all sets of the semiring are mu star measurable. Yeah. So for measurability, take some arbitrary subset E. E is some subset of omega. I take an H in my H. And I take epsilon bigger than 0. And again, I can take E is subset of some HKs, K in no, only K, like this here. So with the HKs are in my H, so E is covered by this. And mu star of E is bigger or equal than some mu of HK minus epsilon K over K. So again, that's the HKs. They cover my E, and they are almost at the infimum for the outer measure. So this here also holds. Now I can write mu star of E plus epsilon bigger or equal than sum over the mu HKs. So that's just from here. Now I can write that's the same as some mu of HK intersection with H plus some over mu of HK intersection with H complement. The reason is that mu here is assumed to be additive, and the union of these two here is HK. And I can continue. This here is bigger or equal than, well, mu star of E intersection H, because these sets here, the union of these sets, are a superset of this here, and the union of these sets here are a superset of E intersection H complement. Now let epsilon go down to 0. And then I have this here. And as we already know, this here is anyway bigger or equal than mu star of E, because E is the union of these two sets here. So that's again subadditivity of my mu star. So all of these terms here agree. In particular, this here is the same as this here, which means that H is measurable. So we have that H is a subset of F star, and we are almost done. We still have to show it's the only measure that agrees with mu and H, but H is a semi-ring, which means H is intersection stable. And we had at the beginning, recall this please. Yeah. If two things agree on an intersection stable generator, they agree completely. So that's the reason for the unique part here. Yeah, the only measure. So that's this here. Okay, one last thing I'd like to mention here. I'm not going to prove this. Please read the manuscript if you want. Apparently, we already showed that sigma of H is a subset of F star. So you can ask which sets are in F star which are not in sigma of H. And this proposition here answers this. And the answer is the difference between F star and sigma of H are only sets N which are null sets. In the sense, you can write all sets in F star as, well, an element of sigma of H minus a null set. Of course, the empty set is also a null set, so sigma of H is a subset of F star, but in general, just A without any null set is an element of F star. That's just for the background. We're not going to use this result any longer, but that's in order to understand the difference between sigma of H and F star. Okay, great. So much for today. Hope to see you soon.